Hi everybody, I'm feeling a little grumpy because my second monitor has stopped working, and so my video is going to be a lot rougher than it usually is because of that. Anyway, so sum properties, this is a short topic, and I hope it will be a straightforward one. The idea is that a lot of techniques in math are about taking something complicated and breaking it down into simpler parts. So in this example, we've got the summation of this. It's not very complicated, but it's a little bit complicated, this sum. So we're going to think about some properties that will let us take a summation of several things and break it down into summations of simpler things. And I think this is going to make a lot of sense by just expanding this, because really summations are just a sum, thinking about what you can do algebraically to the sum and then rewriting it. So here, if I write out the terms, when k equals 1, I've just got 3 plus 7. And then when k equals 2, I've got 6 plus 7, and then so on. And eventually, once k equals 100, I'll have 300 plus 7. So that summation is really just this sum. So let's notice a couple things. First, we could take all of the 7s and rewrite them over here. So I'd have 3 plus 6 plus 9, blah, all the way up to 300. And then all the 7s I'd write over here. And so now I've got two summations. So this one I could already write as the sum of k equals 1 to 100 of 7. Just that part. This part, before writing the summation, let's take out the common factor here of 3. So I've got 3 times, and then when I pull out a 3 here, that becomes 1. Pull out a 3, that becomes 2. That becomes 3, and so on up to 100. Alright, so the last step is to observe that this is equal to 3 times, and I can rewrite that thing as a summation also. So summation from k equals 1 to 100 of just k. And then I'll add to that the summation of 7. So what we have here is my original summation. I'm going to stop writing the bounds here, just because it's taking a long time to write the bounds. You know what the bounds are. So the summation of 3k plus 7 is the same as 3 times the summation of k plus the summation of 7. So you can sort of imagine it like the summation of two separate terms breaks into the summation of each of those terms separately when you add them. If you have the summation of a constant times a term, you can simplify that by pulling the constant out. And the reason why you can pull the constant out is because if you're multiplying every single term in a sum by the same constant, then of course you can factor that term out of the sum, which is the same as pulling it to the outside, and then rewrite the sum as a summation. So that's the general kind of idea behind what we're doing here. Let's write down the properties and appreciate why they're true. And then you'll see the kind of problem that you'll be asked to solve. So one of the major properties is, I'm going to leave off the summation bounds, which is a pretty common thing that you see in a lot of textbooks. Let's just assume that I'm going from some number to some other number. So if I've got the summation of a bunch of terms plus a bunch of other terms like this, that would be like I wrote a1 plus b1 as my first term, and then a2 plus b2 as my second term, and so on, up to an, bn. So obviously, I could separate these and add all the a's first and add all the a's second. So a1 to an would be my first sum, and then I'd have b1 to bn as my second sum, and then I can write those as their own summations, sum of the a's and sum of the b's. So that's the first sum property, is if you have the sum, if you have a summation of two separate terms being added together or subtracted from one another, you can break that into two separate summations. The second summation property is what I just said. If I've got a summation where c is a constant and a sub k are each of the terms, that's the same thing as writing c times a1 plus c times a2 all the way up to c times an. Because c is all constant here, I can pull it to the outside, and then I've just got a1 up to an. And so then I can rewrite this as c times a summation that consists of just each of the a sub k terms. So that's the second property, is being able to pull constants to the outside. All right. Let's do one more. So the last one is, let me start with my summation, okay? 2, 3, 4. Let's go all the way up to like some a sub j, j plus 1, up to n. All right, so let's say I've got a long summation. This is k equals 1 to n. The property I'm about to tell you is that you can rewrite one long summation as two shorter summations. Actually, let's do this. So this would be the summation where k goes from 1 to j minus 1. And then this would be the summation where we go from k equals j to n. And that's equal to the summation from 1 to n, right? So the summation from 1 to the end is the same as the summation up to a certain number, which we're calling j minus 1, and then starting one after that, j, up to the end. And that might seem uninspiring, but we can rearrange the terms here. Let's say we only cared about this part of the summation. If we only cared about this part of the summation, we could say that this part is equal to the entire summation minus the part that goes from the beginning up to here. So if we're interested in the summation from j to n, then that's equal to the entire summation from 1 to n minus the summation from 1 to j minus 1. And this is the actual useful property. Okay, part of the major goal of this unit is not so much that you become master of these facts, although they are pretty basic facts and it would be good to master them. It's more like getting you used to going back and forth in your mind. When you see the sigma, you have to start feeling like this is a familiar friend, like, oh, that's just a sum. So you can treat it like a sum. In a lot of units in calculus, and in the most important unit, the crown jewel of calculus, the fundamental theorems of calculus, you'll need to be able to feel very comfortable with summation notation. So the more you work with it and the more different contexts you think about it in, the better it's going to be. All right, so we've come full circle. Let's apply it. So this is the kind of situation where you might need to apply it. Let's say we've got a complicated summation like 3k squared plus 2k plus 5. And let's say k is going from 1 to 100. So in solving a problem like this, the first step would be to apply those properties to break this down into simpler parts. So first, I could say the summation of, this is like 3 separate terms being added. So I could say this is equal to the summation of 3k squared plus the summation of 2k plus the summation of 5. And each of these summations is going from 1 to 100. But then I could do one step further, which is pull these coefficients to the outside. So I'd say 3 times the summation of k squared plus 2 times the summation of k plus the summation of 5. And now let's go ahead and write back in the bounds. All right, so this should be pretty obvious what it is, I hope, if you think about for a minute what the summation is. Here I've got 100 terms. Each of them are 5, so this is like adding 5 to itself 100 times. So that's the same thing as 5 times 100. So I've rewritten that one. Here I've got 2 times the summation of. This is just 1 plus 2 plus 3 plus 4 all the way up to 10. And so this is a situation where these two are like really basic building blocks for summations, and you would look up equations for what are these two things equal to. So this one, let's pull it out over here, is just 1 plus 2 all the way up to 100. And if you think about that as a basic arithmetic series, that's like, let's see, first term plus last term is 101 times the number of terms, which is 100 divided by 2. So I could rewrite this one as 101 times 50. And then this summation is just 1 plus 4 plus 9 plus 16 plus 25. So it's the sum of all the square numbers. This one you don't know a good equation for, but let's find the book. On page 830, ta-da, there's a box which shows you the equation for the sum of squares and an equation for the sum of cubes. And those are things that you could either look up, or if it was an exam, you would be provided on the exam. Because more we're interested in, can you simplify the larger expression down to really simple building block expressions, which you can then look up the answers for. So in this case, we've got 3 times, and then so n here is 100, because that's how many terms we have. So the equation says 100 times 101, times 201, all divided by 6. This is one that you're actually capable of driving on your own. It's a little tricky. It would take some time to figure out, but you could do it. The sum of cubes, I think, is quite a bit harder. So I'm not gonna actually compute the numerical answer here, but my point is, using the summation properties, you can take a summation of a more complicated expression and then break it into individual parts. And then for the simple building blocks, you look up what the formulas are and you plug it all in, and now you've solved it. All right, I think that's it for this video. Thank you very much.